The calculations of a correlation analysis. If you have two variables, say x and y, and have confirmed using a scatter plot that a linear pattern appears between them, then you may want to calculate the correlation coefficient between them to determine the strength and direction of the linear relationship if one exists. Recall that rho is the population correlation between the two variables, which is an unknown population parameter. We will use a sample from the population to calculate the sample correlation coefficient called R, and we'll use R to estimate rho. The formula for R is R equals the ratio of the sum of the x minus x bar values times the y minus y bar values, divided by the square root of the sum of the x minus x bar values squared times the sum of the y minus y bar values squared. To calculate a sample correlation by hand, it is easiest to show the x and y values in two adjacent columns of a table. Excel is very helpful for this calculation. For example, let's suppose we have a very small sample of 6 points. The x values are 1, 2, 4, 6, 7, 10, and the associated y values are 4, 3, 8, 10, 9, 8, respectively. The next step is to calculate the mean of the x values, which in this case is x bar equals 30 divided by 6, or 5, and the mean of the y values, which in this example is y bar equals 42 divided by 6, or 7. In the next column, we take each value of x and subtract the mean of the x values. For example, the first x is 1. The x bar is 5, so 1 minus 5 is negative 4. Similarly, we can take each of the remaining x values and subtract 5 from each. Those values would be put in a column. We repeat this process for the y values and place those in the next column. For example, the first y value is 4, and the mean of the y values is 7. So 4 minus 7 is negative 3. Similarly, we can do the other y values, subtracting the mean from each. Next, we take each value of x minus x bar and multiply by the associated value of y minus y bar. For example, for our first observation, x minus x bar is negative 4, and y minus y bar is negative 3. When we multiply those together, we get 12. We then do this for each of those values and add them up. This will be the numerator of our fraction of the correlation coefficient. Here are the values summed to 35. Next, we want to square each of the values of x minus x bar and place them in a column. For example, the first x minus x bar value is minus 4. When we square that, we get 16. The next value is minus 3, which when we square it, we get 9. We continue in this way, doing this for all of the values and then sum them. This will turn out in this example to be 56. We do the same thing for the y minus y bar values, squaring each. For example, minus 3 squared is 9, minus 4 squared is 16, etc., and then summing up all of those values. In this case, we get 40. These values are used in the denominator of the fraction. We multiply them together and then take the square root. So 56 times 40 is 2240, so we take the square root of 2240, which is approximately 47.329. Lastly, to calculate the correlation coefficient, we take the numerator, here 35, divided by the denominator, here 47.329, to get the correlation coefficient R equals 0.7395 in this example. Note that Excel has a function called equals correl, that's equals C-O-R-R-E-L, that you can also use to calculate this R value, or you can use statistical software to calculate it as well. Now, once we have a correlation coefficient, we must be careful to interpret its value. It may indicate a relationship, either positive or negative in the sample, but we really want to know if there is evidence of a significant correlation in the population. This is because it is possible for there to be no discernible pattern in the population, but it just so happened that the sample we obtained appeared to suggest a correlation. Therefore, we usually want to do a hypothesis test to test the null that rho equals 0 against the alternative that rho does not equal 0. Note that if the null is true, rho equals 0, that would mean there is no correlation between x and y in the population. And if the alternative is true, that rho does not equal 0, that would indicate there is a significant correlation between x and y in the population. The test statistic is a t-distribution with n minus 2 degrees of freedom, where n is the number of observations in the sample. T equals the ratio of r divided by the square root of the fraction 1 minus r squared divided by n minus 2. In our example, where n equals 6, and R equals 0.7395, we find that T equals 0.7395 divided by the square root of 1 minus 0.7395 squared divided by 4. This comes out to be 0.7395 divided by 0.3366, which is about 2.197. To complete the hypothesis test, we can either calculate a p-value for this test statistic or a critical value using a t with n-2, here 4, degrees of freedom. We can use a t-calculator or a t-table to find these values. Suppose we want to test this hypothesis using a 5% significance level. Then using a p-value approach, the two-tailed p-value for 2.197 on a t with 4 degrees of freedom is 0.093. Since the p-value is greater than alpha, we do not reject the null that says the population correlation is 0. Alternatively, using a critical value approach, the two-tailed rejection region for 5% on a t with 4 degrees of freedom is outside the critical values of minus 2.777 and positive 2.777. Since our test statistic, t equals 2.197, is between these values, we do not reject the null that the rho is 0. Thus, although the sample correlation was positive and fairly large, based on the sample size, we have no evidence of a significant correlation in the population.